Warning: the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to start talking about all the topics that you're going to need as you head into limits for differential calculus. All of this is very theoretical. It is kind of a different in mindset from all the algebra and trig you've done in the past. So you really do have to pay attention to the detail that we're going to introduce here. The first thing I want to talk about is this definition of a punctured open neighborhood. Now, this is often not found in a textbook, but it is actually very important as you go into calculus. So let's talk about it here. A punctured open neighborhood centered at some point A is a set of points within a non-zero radius R of A. Let me go ahead before I read the rest of that and showcase what I mean by that. So you have some interval here. I just drew a number line, and we're going to go ahead and place a number A on it. Now that we've placed the number A on it, we're going to create a radius on that number line centered at A. In other words, we're just going to wiggle to the left and to the right by a distance, some distance we'll call R. And I'll keep it, I'll just measure it out using this ruler here. So let's go ahead and use red for that. Now you could see very barely here, you could see that I've drawn in red these edges to this neighborhood. That's what this interval is actually called in calculus. It's called a neighborhood centered at A, but it's a punctured open neighborhood. And that's critical to note here. The puncture means that it is open in the center. We do not include that central point. And that's actually what I mean here. Let's see, is the set of points within a non-zero radius. When I say a non-zero radius, that means that we're only going to consider the set of points that are not equal to A, but slightly away from A. So all of these points right here, but not at A itself. It's very important to note in calculus, you're not including that central point A. So there is an open hole at A itself. So that is the puncture. When I say a punctured open neighborhood, the puncture is actually just that central point. All the x values that we allow within this interval or this neighborhood centered at A are all the highlighted x values you see there. Now, it is also an open neighborhood. So this is kind of critical because the word within right here is telling us that we're only considering points within that radius, but not at the edge of that radius. So notice on my drawing here, I did not include those endpoints, which are a distance of R away from the central point A. In fact, let me draw that in. So those distances to either side of A are the same distance. And in fact, this point right here on the edge is actually A plus R. And the point on the left edge is actually A minus R. So really we're considering the interval from A minus R to A plus R without the center. Now that we've drawn that out, let's go ahead and finish reading the definition here. In fact, I'll start over from the beginning. So a punctured open neighborhood centered at a point A is the set of points within a non-zero radius R of A. For the purposes of this course and any calculus course you're in, whenever the word neighborhood is used, it is assumed to be a punctured open neighborhood. Now, the definition is actually pretty dense. Even though I kind of summarized it very quickly, it is actually very dense. The first thing I need to mention here is that neighborhoods need not be horizontal. They could be vertical. And as you move into three-dimensional calculus or higher level mathematics, neighborhoods end up being parts of an n space, 3D, 4D, 5D, and so on and so forth. But for our purposes in this course, a neighborhood is just going to be either centered at some point horizontally or centered at a point and then expanding vertically. Now, it's traditional that for horizontal neighborhoods, we use the Greek lowercase letter delta. And so we would say that we have a delta neighborhood centered at A, and these are traditionally, again, horizontal neighborhoods of radius delta. So in this case, if this neighborhood has radius delta, it includes all those highlighted or scratched out red points except for the edges, and it does not include the center, but otherwise it includes everything else. It goes from A minus delta all the way to A plus delta. So you have this kind of wiggle, symmetric wiggle on either side of A, and that wiggle is of size delta in both directions. Well, we also have a similar definition for the vertical neighborhoods, and these are called epsilon neighborhoods. And just like we would center horizontal neighborhoods at A, we'll go ahead and center vertical neighborhoods about some value. We'll call that capital L because it's very traditional in calculus to do that. So in this case, we have a horizontal or vertical neighborhood centered at L of radius epsilon. That would include everything between the top and bottom there, which means L minus epsilon to L plus epsilon, but it will not include that puncture, that open hole in the center. So again, when I say neighborhood or your instructor says neighborhood, they really mean it's an interval, it doesn't include the center, and it does not include the endpoints. And that actually summarizes pretty much all the other stuff that I was going to mention there, which is that each of these neighborhoods have punctures, right? The center is punctured out, just like maybe a hole punch. You punch out the center of these neighborhoods, and they're also open, right? The edges are open. So that's what this says right here, and that's what that says. So they're all neighborhoods, and they are punctured in the center, and they're open at the edges. That is critical to understand for calculus. Now, the intent of this video is just to introduce some very important definitions before we move into actually doing calculus. And you may think that you know what infinity is and what an infinite thing is, or an infinite object is, or what infinitesimal means, but in reality, most people don't. They think infinity is just some large number. Infinity is only a concept. And so my definition here is as good as I can get with this. A value that is greater than any assignable quantity or countable number is called infinite. The notation we use for such quantities is this symbol right here, also called the lemniscate. And if the quantity is negative, then we use the negative of the lemniscate. In other words, negative infinity. But it is critical to note that infinity is not a number. And that's why I use quotes on the word value here, because in reality, infinity is not even a value, it's a concept. And that's all that infinity is. Infinity is a concept, not a number. This is why you never use inclusion notation on infinite endpoints of intervals. This is a mistake that a lot of algebra students will do when they're writing out intervals. Let's say you have a number line and you want to shade everything starting at 3, including 3, let's just say, and going on to quote unquote infinity. I have taught for years and seen this all the time. I get a lot of students that love to write, oh, this is an interval from 3 to infinity, and they'll include the edge on infinity. Infinity is not a number, so you cannot include it in your set. Infinity is just a notation that says this value is without bound. It's massive. So this inclusion notation is incredibly improper. And so you would use exclusion notation there, the parenthetical notation rather than the bracket notation. The concept of infinity ends up confounding students a lot throughout calculus because it's such an interesting concept. It really engages the imagination, and you think that you really do get it, and then all of a sudden something happens and you just don't. One of the most confounding examples would be when you deal with some level of infinity or some type of calculus object that ends up looking like infinity minus infinity, and that is not 0. And that is not finite, it's called indeterminate. We don't know what it is. You have to do a little more investigation to figure that out. And it always changes, by the way. It's not the same. It just depends upon what question's being asked. And so it's very important to note when you're playing with infinity, arithmetic breaks down. And that's why we have calculus. Well, now that we've discussed infinity and the infinite, we can now talk about what it means for something to not exist within calculus or within mathematics itself. So in mathematics, the notation DNE stands for does not exist. And that is actually reserved for very special circumstances. It's not every time that you don't get an answer, you just say does not exist. That's actually not true. That notation is used when something in calculus is simultaneously not finite and not infinite. And so you might say, wait a second, I thought that something being finite or infinite was like an on and off switch. Either something's finite or it's not. It's infinite. And that's actually not true. And that's probably the first really weird thing about calculus is that you start dealing with things that have this trifecta of options where it could be finite, infinite, or it just could not exist. And a good example of that would be, for example, the sinusoidal function. I think most people would agree that this is approximately the sine curve or the cosine curve, doesn't really matter to me, but it goes on forever and ever and ever. When you ask the question, what's the value that that sine function takes on as x goes on and on forever, off to infinity? Notice I included that word infinity that we just talked about a few moments ago. You will not be able to tell me because it doesn't become something finite. It wobbles between a positive one and a negative one in value. And if you keep going forever and ever, it keeps wobbling forever and ever. And you cannot say what its value is because it cannot be determined. So it does not exist, the value of the sine function that is, as x goes to infinity. So just letting you know that there are three options in general for the values of things within calculus. Some value might be finite, or it could be infinite, or if it's neither of those, it just doesn't exist. And I don't want to get into too much detail about that other than to say you need this definition before going any further. So in the next video, we'll start dipping into this idea of infinity and does not exist, and we'll really solidify the concept. I'll see you there.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.